Hi there, Ivar. In this video, we're going to look at derivatives of multivariable functions. If we consider z to be a function of x and y, the question is then, what is the derivative of z, or what is the rate of change of z? If we have a 3D plot, how does z change in terms of 3D? Well, what happens is that we consider z in terms of the rate of change with respect to each individual variable. In other words, we would have the rate of change of z with respect to x and with respect to y. So you can see that we have used the notation day. So this means that the derivative is taken with respect to a single variable, but in a multivariable function. Whereas dy dx was the derivative of a single variable function, day represents the derivative of a function of one variable, but in a multivariable function. We can also have second derivatives. So we would take the first derivative and take the derivative of it again. And we would do the same of the other variable. We can also take this first derivative and then do it with respect to y. So we will be taking the derivative with respect to y of day z dx. So what this looks like is the second derivative of z that was initially taken with x and taken of y. And the same would be done with respect to x. So we would find the derivative of x of day z dy. And this would be the second derivative of z, initially taken with y and taken with x now. So these are called mixed partials. As a general rule, we expect the mixed partials to be equal. So that is day squared z dx dy is equal to day squared z dy dx. In terms of an example, we could look at z is equal to x squared plus y squared. The derivative of z with respect to x is simply 2x. We treat y as a constant, and the derivative of a constant is equal to 0. In this case, y squared is seen as a constant, and therefore its derivative is 0. And then we would do the same with respect to y. So day z dy is simply equal to 2y. In this instance, we have treated x as the constant. So x squared is just a constant number, and its derivative is equal to 0. That's why day z dy is equal to just 2y. We have taken the derivative of y squared. So what does this mean geometrically? Well, if we plot the function z is equal to x squared plus y squared in 3 dimensions, so please excuse my poor drawing. We see that this function looks as a champagne glass, which is what we have discovered in the last video. So if we're saying that y is equal to a constant, right? What are we saying? Well, we can choose any value of y. Let's just say y is equal to 2. And we take a slice, or we take a snapshot of this function where y is equal to 2. So what would that look like? It would look something like this. We take a slice at 2 and we cut it out of the graph. So imagine now we're taking like a little saw and just extracting out what the graph looks like where y is equal to 2. So imagine that this graph is being cut out at y is equal to 2. There's y is equal to 2 here. And it's being cut at that point. This entire little slice is taken out. And then if you plot that slice, right? So we plot that little slice. What does it look like? Well, it's a plot of the xz plane. You can see that this is z and this is x, and that little slice is the xz plane. So we have x and we have z. What this looks like, what it would look like if we were to take a slice, is that it's a parabola. And we have chosen the value y is equal to 2. What that looks like in terms of the equation is that z is equal to x squared plus 4, because the equation is y squared and 2 squared is 4, so z is equal to x squared plus 4. And this is very familiar because this is what a parabola is, which is very well studied in earlier courses of maths. So the question is, day z, day x, what are we saying here? We're saying that it's equal to 2x. We're saying that on this specific plane with this constant variable of y, we're saying that this is how z changes with x. Z changes with x linearly, 2x. So this is how z changes with x. So that's what we mean when we say we keep the variable y constant. So if we take day z, day y, what we're doing is we're making x constant. So we're choosing a value of x. We can choose a value of x here. Again, we can choose the value 2, and then we take a snapshot of it. And for each snapshot, we will have, this is how z changes with y, or in the instance of x, this is how z changes with x. So if we continue with this example, then we can take the second derivative, day squared z, day x squared, and if we find the second derivative, we see that this is just equal to 2. Of course, the derivative of x is just 1. And then we find the derivative of z with respect to y, and that's equal to 2 as well. And then if we take this derivative and then find the derivative of that with respect to y, in other words, we find the mixed partial, day squared z, day x, day y. So the derivative of this with respect to y is just going to be 0 because there is no y in this function. It's just x, and x is being taken as a constant. And if we do the same, with the mixed partial, where we take the derivative of z, day z, day y, and then find it with x, we find that this is 0 as well because there is no x inside this equation, and therefore y is taken as a constant, so this is 0. And we see that these both are equal, which is what we said is the case very generally. So in the next video, we're going to find the derivative of a more complex function, and we will also revise the chain rule and the product rule.